Welcome to Code Report. I'm your host, Connor Hoekstra. A big thank you to everybody that subscribed over the last week. If you have any feedback or suggestions on ways that I can improve these videos or things that you'd just like to see on this channel, please leave a comment down in the comment section below. With that said, let's take a look at the contest that happened last week. Taking a look at the contest that happened last week, once again we had 3 Codeforces contests, one on Monday, one on Wednesday, and one on Friday. We had the 1 hour long HourRank Contest 26 put on by HackerRank, and of course we finished off the week on Saturday with LeetCode Contest 70. So here are the top 10 leaderboards for each of those 5 contests. Note that round 459 and 460 were only for Division 2 on Codeforces. And I guess notably this week, Yui took the top spot in both the HourRank and the LeetCode Contest 70. So the problems we're going to be covering in this video today are problem 3 from LeetCode Contest 70 and problem 2 from HackerRank HourRank 26. And then later today / this week, I'll be posting videos for the remaining 3 problems from the LeetCode Contest and also problem D from the Codeforces Round 460. So let's take a look at our first problem. LeetCode Contest 70, problem 3, entitled Swap Adjacent in LR String. The problem states, in a string composed of LR and X characters, a move consists of either replacing one occurrence of XL with LX or replacing one occurrence of RX with XR. Given the starting string start and the ending string end, return true if and only if there exists a sequence of moves to transform one string to the other. So let's restate this problem. We have 2 strings start and end consisting of the characters XL and R. You can swap L and R only with X, not with each other. L you can swap to the left, R you can swap to the right, and the question asks us to return true if you can transform start to end. And note that the limits on the length of start and end are between 1 and 10,000. Looking at our first example, we have the start string XLRX and the end string XRLX. And we can see that because the L and the R are next to each other, we're not going to be able to swap them in order to get start to end. So this pair of strings will return false. However, in a modified example that's similar to the first one, in this string we have the start string XLRX and the end string LXXR. So this one clearly we can swap the first 2 characters, the L with the X, and the second 2 characters, the R with the X, in order to end up with our end string. So this example will return true. So we can see that based on the order of our L's and R's, if we can see that they are not in the same order after we remove the X's, we're going to return false in all of those cases. And that's because we can only switch R's with X's and L's with X's. We can't switch R's with L's. So if the L's and R's are out of order, we just know we're not going to be able to get from start to end. So there's a couple more examples we need to look at to inform the second half of our algorithm. And we can see here that although the order of our L's and R's are the same, for the first example it's just one L and the second example is just one R, because we can only move L's to the left and R's to the right, we always have to have a greater number of L's in our start string up to a certain character I when looking at both start and end. And the same thing is true except in the reverse for R's. And with these facts, we can now look at the code. And these 2 return false, obviously. So here we have our can transform function. It takes 2 strings, start and end. So the first 4 lines of the algorithm are going to take care of the first half that we looked at in our examples. So basically here we're just constructing 2 temporary strings, s and t, and all we're doing is removing the x's from start and end. And then we end up with start and end basically reduced to just the r's and the l's. And if those 2 strings are not equal to each other, we will return false. And then for the second half of our algorithm, we're going to keep track of the running totals of the r's and l's in both start and end. So that's pretty straightforward. We're just initializing here, and then for every element doing a post increment on the corresponding running sum. And if at any point the r's in end are greater than the r's in start, or the l's in start are greater than the l's in end, we can return false. And this algorithm is, of course, linear, because this is linear, and this is linear as well. Moving on to problem 2, Cloudy Day, from HourRank 26, a contest put on by HackerRank. The problem states we are given towns on a horizontal line, and those towns exist at one point, and clouds that also exist on the same horizontal line, and they exist over a range of points. A city is sunny if it is not covered by a cloud, and the problem asks us to return the maximum number of people in sunny cities given that you can remove one cloud. So the constraints are n, the number of towns, is between 1 and 10 times, or 2 times 10 to the power of 5, which is 200,000. M is the number of clouds, is between 1 and 10 to the power of 5. And the locations of clouds and towns is between 1 and 10 to the 9. So there's a little diagram in the middle. You can sort of see a visualization. And in the bottom right here, we can see that the first problem in HourRank was very, very easy. It had a 99+% success rate, and then there was a huge drop-off. And this is pretty large for a medium-level problem, so there was quite a few people that had difficulty with this. So let's take a look at an example. So in this example, we have 6 towns represented by the blue dots and 2 clouds represented by the gray rectangles. And underneath each of the towns is the population of that town. And so we can see that 2 of our towns, the first and last town, exist not under any clouds, meaning that they are by default sunny. And then the 4 other towns exist either under 1 cloud or under 2 clouds. So the first thing we need to notice about this problem is that if a town exists under more than 1 cloud, we can ignore it, basically, because regardless of the cloud that we remove, it's still going to end up being under a cloud at the end of the day. So the 2 middle towns, town 3 and town 4, we can just ignore for the purposes of what we're looking for in this problem. And then the second thing we need to notice is that we basically only need to keep track of 2 numbers. We need to keep track of the sum of the population of sunny cities by default, the cities that just aren't under any clouds to begin with, and then we need to keep track of the maximum number of people, so the maximum population under 1 cloud, and that 1 cloud only while we're doing our algorithm. So if we had multiple clouds and none of them overlapped, we would just need to figure out which cloud is covering the most number of people, and that is going to be the number that we can add to the free people already. So we're going to have 2 numbers basically. Free people, in our example, that's going to be equal to 10, the sum of the first and last city, and then the maximum people we can add, which in our example is going to be equal to the sum of the second and fifth city, because they're only under 1 cloud. And the third structure I have here is an unordered map, and that's going to keep track of the current number of clouds that we are underneath. So let's take a look at how this example would work sort of visually. So we start at the beginning. We have a town that's not under a cloud, and we can tell by looking at the size of our unordered map. Sorry, I said set earlier, map. And because it's equal to 0, we can just add this to free people. We move to our next point on our horizontal line, and we can see we're at the start of a cloud, so we're going to insert into our map cloud number 2. And the value in our map is going to be the current number of people underneath that cloud that could be added, so that exist underneath the cloud only when that cloud is the only one in our unordered map. So we move to the next element. Here we are under a cloud, so we're going to check current cloud size is equal to 1, and then we are going to add the population to the value of the only item in our map. So that is going to be set to 10, and then every time our current cloud size is equal to 1, we're going to set maximum people that we can add equal to the maximum of the current value and what the new value that we just added to in our map is. Then we move to the next point on our horizontal line. The first thing we're going to do here is add a new cloud to our map, because we need to process that before we look at any towns. We're going to do that. And now, because the number of clouds that we are currently under is greater than 2, we aren't going to do anything to the free people or the max people we can add. So we move to the next point on the horizontal line. The first thing we do here, again, is look at towns, because now we have an end of a cloud, but we still need to process towns before we can remove the clouds from our map. So we are going to do nothing for this town, and then we are going to remove cloud ID 1 from our map. Then we're going to move to our next point in our line. Now we're back to only having one cloud, so the size of our map is going to be 1, and so we are going to do a plus equals to the value of the only item in our map. And once again, we are going to set max people can add equal to the maximum of its current value and the result of the plus equals we just did on the value of our cloud in the map. And we move to the next point on the horizontal line. This is just going to consist of removing cloud 2 from our map. And then finally, once we get to the end of our horizontal line, we no longer have any clouds in our map, so we are going to do a plus equals to free people. And then at the end of this, all we're going to do is return free people plus max people can add. So let's take a look at the code. We're going to look at this code in 2 different parts because it's a bit much to show on one slide. This first is just showing basically the initialization. So we have 4 vectors. The first one, people, represents the number of people in each one of our towns, so the population of our town. The second vector is the position of our town. The third vector is the middle position of each cloud. And our fourth vector is the plus or minus range. So if we're given a cloud is at position 5 and the corresponding range is 1, that means the cloud exists from position 4 to position 6 inclusive. And so at the top of our function here, we are declaring 3 multi-maps and 1 unordered map. So we discussed the unordered map. That's keeping track of our cloud IDs that we're currently underneath and the number of people that exist only under that cloud while there's only one cloud. And our multi-maps are basically for sorting our positions. So they're for sorting our towns and the start and end of our clouds. And so for the cloud, the value in our map is going to be the ID of the cloud. And for our towns, the value is going to be the population. And I should note that if you haven't seen a multi-map before, it's exactly the same as a map. The only difference is that you can have multiple keys of the same value. Their interfaces are roughly the same. There's a few things you can't do with a multi-map that you can do with a map. For instance, bracket operators aren't defined for multi-maps. But the insert function and the find function, they work similarly. So we are going to construct our multi-maps in the next 3 lines by just inserting our make pairs of positions for the cloud start, which is the position minus the range. Cloud n is position plus the range. And we're just using the index of our cloud as the ID. And for our towns, we are just going to be using the position and the population. And the next, or the final 4 lines on this view are just the initializations of our variables that we are going to be using in our algorithm. As you can see, free people, max people you can add, and some iterators so that we can move through our multi-maps. Moving on, this is where we do all of our work now. So we're going to do this loop while we still have towns left to process. And the first thing that we are going to do is we are going to check while we don't have to process a cloud, we are going to process towns. So our first statement, if current cloud size is equal to 0, that's the easy case. We just add the population of our town, arrow operator second, we do a plus equals to free people. Else, if the current cloud's dot size is equal to 1, then that's where we have to add the population of the town to the value of our cloud that is being stored in our map. So because we know that the size is equal to 1, we don't have to loop here. We can just look at the only cloud in our map. So we do the plus equals to the value, and this is the line where we are setting our max people can add. So we're setting that equal to the maximum of its current value and the value that we just did the plus equals to. And we continue to do this until we need to process a cloud. And so once we hit a cloud that needs to be processed, first we are looking at clouds we need to add. If we need to add a cloud, we insert it using the bracket operator, setting the current value to 0 because we don't have any towns under it at this point. And then we do a plus plus on that iterator. And if we have the end of the cloud that we need to process, we are just going to erase that iterator. And so if we continue to do this, we will end up with the correct values for free people and the max people we can add. You should note that an important place to pay attention to is these less than and less than equal to operators. We need to use less than when we are dealing with the start of clouds and less than and equal to when we are dealing with the end of clouds when looking at towns, but the opposite when we are processing them. And that's, like I said, because when we're getting rid of a cloud, we first need to process a town that might exist at that end location. And when we are adding a cloud, we need to do that first. So the complexity of this problem is linear for the second half, but n log n for the first half, because the insertions are log n and we are doing n of those insertions. So the complexity of this is going to be n log n in the size of our towns vector, which can be up to 2 times 10 to the 5th. Taking a look at our contest that we have coming up next week for the week of February 5th to February 11th. Starting tonight at 2 a.m., we have a week of code 36 starting. So for the whole week, we are going to have a problem released daily at 2 a.m. That you can solve. That'll be put on by HackerRank. On Thursday, we have round 461 by Codeforces. On Friday, we have a 48-hour Goldman Sachs code sprint starting at 1:30. On Saturday at noon, we have a top coder, SRM 729. And of course, we're finishing off the week with the LeetCode weekly contest, Contest 71. And finally, these are some analytics that I thought I would share because I like statistics, and this is pretty cool, I think. So now that I have people watching my videos, once again, thanks for subscribing, everyone that did. I get analytics on all of the demographics of the people watching my videos. And I think up till now, I've had people from 56 different countries tune in to watch at least one part of one of my videos. And here are the top 10 countries in terms of watch time minutes for my content. So thank you to everyone for watching all around the world.
That's all for this week. Once again, if you have any feedback or suggestions on ways that I can improve these videos, please leave a comment down in the comment section below. Or if you have any improvements to the solutions that I showed in this video, you can also leave a comment and I might show it in a future video. If you like this video, hit that like button. And thanks for watching. I'll see you in the next video.